fronts out here.
We do need
Someone,
to
really has the boat right now.
One was the front and one was like this.
Okay, we'll talk to you in a bit. The COOLroom standing by on 79.
The COOLroom is a place for scientists to talk. On a college campus, physicists are in one building, biologists in another. They don't work side by side, so it's hard for them to communicate. In the COOLroom, we work together all day long.
Space science has followed this practice for over 50 years, and that's what NASA's mission control is. It's one big room, all the scientists working together receiving data from outer space. On the other hand, ocean sciences has really lagged behind until now.
The COOLroom is where we assemble the data to predict the underwater weather. The idea for the COOLroom really began with Fred Grassley.
In 1986, Chris Van Alt and I developed the idea of an underwater weather observatory. This is a lot like weather observatories on land that we use to predict the weather. Rutgers acquired this Coast Guard lifeboat station just a little bit north of Atlantic City. This is where we began assembling the Coastal Ocean Observing Laboratory, or COOL, as my colleagues like to say. This is where the name COOLroom came from.
Here on Earth, we live in and around two fluids, the air and the water. They're both fluids, one is just a little thicker than the other. And because they're both fluids, they're constantly changing and moving. That change is what we call the weather.
For a long time we've been able to predict atmospheric weather, but it's only been recently in the last few years with the advent of new technologies like robotic subs and satellites in space that we've been able to start predicting the underwater weather.
To predict the underwater weather, we have to pull together a wide range of information. That's what happens in the COOLroom.
Information is compiled from 4 sources, the first of which comes from satellites in space.
Here at the COOLroom, we can download data from 5 different satellites that show us information on ocean temperature and ocean color. The ocean temperature information is used by fishermen, and it's used by sailors. The fishermen can use it to help them find fish. The sailors can use it to help them navigate the sea quicker. Upwelling events are what cause the beaches of New Jersey to be cold during some summer days. Here's an image that shows upwelling along the New Jersey shore. The blue area that starts at the beach is the cold water rising. Offshore is warmer yellowish water. The yellow temperatures are about 75 degrees, while that upwelled cold water is about 55 degrees along the coast. Here are 2 images that show us what upwelling is. The image on the left is a surface view of the warm water offshore and the cold water rising near the beaches. The image on the right is a cross-section of the ocean that shows us the cold water rising from the bottom and moving to the surface.
The second source of information for the underwater weather comes from aerial surveys.
This is the Antonov. It's an AN-2. It's a Soviet-designed aircraft, and they've been building them in the Eastern Bloc for quite a few years. And we chose this aircraft for a number of reasons. It goes very slowly, which is one of the features that we like since we're trying to catch a lot of photons coming back from the water, which is actually a pretty dark surface.
And the aircraft data allows us to get higher resolution, better quality data that we then use for future development of new satellites in space.
That's the camera. We've got another little video camera, so we just shoot video straight for a couple hours.
Ocean color is used to measure the phytoplankton distribution, the suspended sediments, the river discharge, bottom depth, bottom bathymetry types of problems that we have for coastal problems. CDOM, color dissolved organic material.
What we're looking at is light. So we have the camera just measures in the visible part of the spectrum, and so we get the light that comes from the sun, goes down into the water and gets scattered and absorbed in the water, and then comes back up to our sensor.
We're based at Stennis Space Center down in Mississippi, and we come up to the Rutgers Field Station because there's a number of scientists from all over the country that come here. It's a good collaborative effort going on here.
The third source of information for the underwater weather comes from the ocean surface.
One of the major components of the network are the surface ships, this being one of them. We have a profiling cage with a number of instruments on it. From these instruments we get various biological, physical, and optical data, which is fed directly back via microwave to the COOLroom and then put on the website there.
Another source of sea surface data that we're collecting here comes from this instrument. It's a hyperspectral radiometric buoy, and what we're doing with this is measuring the incoming light from the sky as well as light coming up through the water column in the ocean. And what this instrument does is it gives us an estimate of ocean color, surface reflectance, which is the same information that our satellites are collecting. We collect this data, we beam it back to the COOLroom, and it's put up on our webpage so all the other ships can look at it in real time.
CODAR stands for Coastal Radar. It is a radar system that uses radio waves to measure surface currents and significant wave height. Here's an example of one of the maps of surface current that CODAR gives us. The direction of the water movement is shown by the arrows. The speed at which the water is moving is shown by the length of the arrows and also the color of the arrows.
The fourth and final source of information for the underwater weather comes from underwater sensors.
The nodes are two big structures offshore that are full of sensors. They're located just beyond the sandbar and connected to the COOLroom by a cable.
A node is the place where all the information is initially accumulated. This is the guts of a node that's out in the ocean that has all these connectors that people can hook up to. This is an oil-filled electronic case. This is a suite of sensors that moves up and down in the water column. There's a cable that's wrapped up on a winch, and as the water flows by, you get a changing picture of what's happening in the ocean. All of this information goes through our electro-optical cable 11 kilometers out from the ocean, and it goes back into the COOLroom, into the dozens of computers, and all goes out on the internet for everyone to use all over the world.
One of the more futuristic elements of the program involves underwater robots.
This vehicle is called the Slocum Glider. It's an electric-powered version. It's named after Joshua Slocum, who was the first person to sail single-handedly around the world. You can see the vehicle is about 6 feet long. It's got a tail fin with 3 antennas in it, GPS, the RF modem, which is how we communicate with it, and a satellite service. You can see the wings here on the side. The way the vehicle operates is it descends through the water by changing its ballast, then ascends again, and with the fins we can actually fly along and glide a course. We head from waypoint to waypoint collecting data such as temperature, salinity, and depth. The data is then transferred to the COOLroom. They assimilate that into models, and we decide new missions for the glider. Basically, this is untended for those 30 days, just running around out there. At the end of that time, we go pick her up, reset the batteries, put her back out again.
The second example of underwater robots is the REMUS, which stands for Remote Environmental Monitoring Underwater System. REMUS are smart robots that can be released into the coastal ocean and patrol for up to 1 day. Scientists can later recover the REMUS and then analyze the data it collects.
One of the good examples of the way all this technology works together was last year when we temporarily lost one of our REMUS vehicles.
The REMUS doesn't float very high out of the water, so it's very difficult to see.
When the call first came in, everybody was running around trying to figure out what to do. We'd never lost a vehicle before. We didn't have a procedure.
Well, I think the group that was running the vehicle was a little bit stressed.
We're all sitting there looking at each other, and we decide, let's go into the COOLroom, see what's going on in the ocean. That's when we started logging into our instruments and carefully going through the data, seeing what the ocean's doing in the vicinity that we lost it.
Using the CODAR fields, Scott Glenn was able to piece together where that vehicle might be.
We had frantic people on the radios. Everybody was looking for this lost instrument, you know, more expensive than your house, and suddenly a whole scientist's life work is lost at sea. How do you recover it?
Between Scott and I, we had laid out the CODAR field projections, and knowing the last point we lost it, we could determine where it would potentially be. You know, there's still some element of kind of black magic that goes into it.
We were able to then send an airplane up to the north that flew in along the line, heading right for our Met Tower. It was able to go in, fly right over the vehicle, and vector the boats in directly. The vehicle was recovered with no loss of data. They fixed the vehicle the next day, and it was back in the water.
All this information comes into the COOLroom, where it gives us the present condition of the ocean. That's then fed into our models that predict the underwater weather.
I think one aspect of our program that we're particularly proud of is that we're able to give back to the general public. We've created a website that gets over 50,000 hits a day, over half of which are AOL.com users, not just geeky scientists.
At our website, fishermen can look at satellite maps of water temperatures and phytoplankton blooms to tell where the fish should be schooling. Boaters can look at CODAR images to tell where the surface currents are. And swimmers can look at our upwelling warning index to tell whether the surface temperatures could soon be dropping.
And all this comes from the COOLroom. But the concept of the COOLroom is constantly changing, just like the weather. It's much larger this year than last year, and next year it'll be even larger. And in a not too distant future, it will look like a NASA mission control room.
The COOLroom is becoming increasingly sophisticated. We would really like to sense the ocean environment in the same way that ocean plants and animals experience it. Other COOLrooms will have a similar goal and are beginning to be linked throughout the U.S. The result will be a continuous network of coastal ocean observing system control rooms. We expect this to revolutionize the way we work and play in the oceans.
Okay, got it.
Where it was drifting. Did you get that? That's the greenhead fly experience here at lovely Tuckerton.
The Passionator. Are we ready for the Passionator? The COOLroom is a place. Not that much Passionator.
The largest scale source of information for the underwater satellites.
There it is. It made its appearance.
Oh my God!
Over half of which are AOL.com users, not just geeky scientists.